If an object can change its angular velocity, this rate at which it's changing its angular displacement over time, what's happening is it has experienced angular acceleration. And here's how we would define this. Angular acceleration is Greek letter alpha, that stands for angular acceleration. It's just the change in angular velocity, which remember is omega, with respect to time. So that's how we can define angular velocity. Here's an example problem. Let's say we have a wheel that starts out from rest, and its angular velocity increases until it gets to 30 per second. That's 30 radians per second, and it takes 10 seconds to do that. What's the angular acceleration? Well, remember our definition is angular acceleration is the change in omega with respect to time. Well, omega started at 0, says started out from rest, and it got up to 30 per second. So that is the change in omega. That happened in 10 seconds. So if we take 30 divided by 10, we have 3, and the units are radians per square second, or just per square seconds, because radians really are unitless. An interesting question to ask would be, what's the relationship between angular and linear acceleration? That might develop a tool that could be useful in problem solving for us. Well, here's what we know about angular acceleration. It's equal to the change in omega with respect to time. And here's what we know about omega. Omega is defined as velocity over r. That was one of the relationships that we got that tells us what omega is. So if we substitute, the radius wouldn't be changing. So delta omega, the change in angular rotation, would have to be due to a change in velocity. So delta omega would be delta v over r. Plugging that into our definition of alpha, here's what we'd come up with. Alpha is equal to delta v over r over delta t. But we could rewrite that. We could say alpha is equal to delta v over delta t times r. But delta v over delta t, we know that that is acceleration in the linear sense. And so we could make a relationship here that says alpha, angular acceleration, is the linear acceleration divided by r. So that is a useful relationship that might come in handy. You may already have noticed this, but there are some analogs. An analog is like a parallel between translation, linear motion, and rotation, motion around the center of an axis. Here are a couple of them. Velocity is change in distance over change in time. But we have angular velocity as well, and the analog for distance in angular motion is theta, or angular displacement. So that's an analog. Another analog is that in rotation, alpha is equal to delta omega with respect to time. So omega is an analog for velocity. Theta is an analog for distance. If you think about it, we can create analogs for the two motion description equations that we've been using a lot in translation also. Think about this one. We have Vf equals the square root of Vi squared plus 2 times acceleration times distance. Well, here's the analog for rotation. Final omega is equal to the square root of initial omega plus 2 times not a but alpha and not d but theta. We also have a distance formula. Distance, remember, is equal to initial velocity times change in time plus acceleration over 2 times change in time squared. Plugging in our analogous values, distance is theta. That's equal to not Vi but omega I times delta t plus not a over 2 but alpha over 2 times delta t squared. Well, here's where you could possibly use some of these analogs to solve a problem. This says a wheel starts out from rest. So starting out from rest, that means initial omega is 0. It reaches an angular velocity of 30 per second in 10 seconds. So this is a final omega. And 10 seconds, that's a delta t. The question is, through what angle did the wheel turn during the acceleration? Well, here's what we know. During an acceleration, theta is equal to initial omega times delta t plus alpha over 2 times delta t squared. But we've already established that omega initial was 0. So that means that we could write theta is equal to alpha over 2 times delta t squared. Well, the angular acceleration here is the same as the acceleration in the last problem. We already figured that out, and that was 3 per square second. So that means theta is equal to 3 per square second divided by 2 times 10 seconds quantity squared. This will come out to be a unitless number. The square seconds are going to cancel, and the numerical answer is 300. What it means is 300 radians is the angle that it went through. Here's another question. A potter's wheel is rotating at 30 RPMs. So 30 RPMs is an omega. And we could call that an omega initial here because the potter stops kicking it and then there's a change. So it coasts to a stop. Friction has caused it to come to a stop. That means omega final is 0. And that happens over the course of 2 minutes. So that'd be a delta t. 2 minutes, of course, is 120 seconds. Question is, what's the angular acceleration on the wheel in per seconds? Well, per seconds has a unitless angle measure, so we're going to have to get these RPMs into radians. So let's do that. 30 revs per minute is what RPMs really means. And we know that there are 2 pi radians per rev, so that will give us radians per minute. And we also know that a minute is 60 seconds. So when we do this calculation, we find out that its initial omega is 3.14 per second. That's omega initial. What we're trying to find out here is alpha. Well, alpha is just the change in omega with respect to time. And we know that the final omega is 0. So the change in omega is just 3.14 per second minus 0, or 3.14 per second. This happens over 120 seconds. And so we have units of square seconds. And when we do the arithmetic, we get 0.0262 per square second. Well, we know for translational motion that the F net, the net force, translates to an acceleration through this equation. F net equals m times a. Would it be also true to say that torque net is equal to m times alpha? Would that be true? Is there a direct analog there? Because force and torque would be translation rotation equivalents. So here's a question. Can we make this direct translation to an analog for torque and angular acceleration? So is it true, in other words, that F equals ma is an analog to torque is m times alpha? To explain this, let's think about something that will require a little more space. So let's switch formats. Let's imagine that we have 2 masses. They're identical, and they're describing rotation around 2 different points. Let's say they're attached to the center of rotation by a rod that's stiff, that can't bend, and it's imaginary. It's also massless, so it's not part of anything. The only question is, does where this mass is affect torque, the necessary torque? Let's say that this is going to undergo an acceleration we're going to call alpha. So this is going to be forced in order to have this happen by some force, and that force will be equal to m times a if this has mass m. And the torque then could be figured out because this will be, let's call this r, this distance of rotation. So this thing is going to rotate like this in this circle sort of around its imaginary center. Now let's think about a different object, and this object now is rotating around a circle that's twice as big. So same kind of a motion, but that's 2r, not r. And there's going to be a force that's going to push on here that's going to be equal to its mass times whatever the acceleration is needed to make this go at angular acceleration alpha. So let's call this F1, and let's call this A1, and let's call this F2, and let's call this A2. The masses are the same. It's the same object, m. Well, let's think about what's happening here in terms of the symbols and the things that we know. First of all, alpha 1 for object 1 here, that's going to have to be equal to A1 over R, because alpha is A over R. Alpha 2 is going to have to be equal to A2 over its radius, but its radius isn't R, it's 2R. But these are supposed to happen so that the two alphas are the same. They're supposed to have the same rotational acceleration. So alpha 1 equals alpha 2. Well, if alpha 1 equals alpha 2, that means A1 over R would be equal to A2 over 2R. Well, the only way that that can be true is if A1 twice is what A2 is, because then the 2's would cancel out and you'd have the same angular acceleration, A1 over R. So that means 2A1 is what A2 is. So let's go back up here and look at the torque that would be needed. Here, torque would be equal to M times A1, that's force, times the lever arm, which is R. Here, the torque would be equal to M times A2 times 2R. But remember, A2 is equal to 2 A1s. So that means torque here is equal to M times 2A1 times 2R. Or torque is equal to 2 times 2 times M times A1 times R. Well, MA1R, that's torque 1. So torque 2 here is 4 times as big as torque 1. Well, let's imagine that we had a third situation. Let's say we have the same mass. It's rotating about a point. Same size mass. Again, it's a rigid, massless rod. But this time, it's 3R away from the center of rotation, so it's spinning around this way. And we're going to once again require that it has the same angular acceleration as the original. Well, to make that acceleration happen, we need a torque. And that torque is going to be provided by this F. We're going to call this F3, let's say, and that's equal to mass, same mass, times acceleration 3. Well, if we think about the angular acceleration, for the first one, it was A1 over R. For this one, it's going to be A3 over 3R. The only way A3 over 3R can be the same as A1 over R, just like we saw last time, is that A1 has got to have a relationship to A3. And here's what that relationship is. A3 must be equal to 3 A1s, because if that's the case, 3 A1s over 3 Rs comes out to the same angular acceleration, A1 over R. So the torque for this third situation is equal to force times lever arm. So force is M times A3 times 3R. But A3 is 3 A1s. So it's M times 3 A1s times 3 Rs. Here's what that means. Torque 3 is really equal to 9 times M times A1 times R. But M times A1 times R, that was torque 1. So torque 3 is 9 times torque 1. So we see it not doubling when the radius doubles or tripling when the radius triples, but we see it going up by a square of the change in radius. And that's going to turn out to be significant. So the answer to the question is no. You can't say that F equals MA has a direct analog that says torque equals just M times alpha, because it depends on two things. So this analog isn't really true. It depends on the mass. That's certainly true. A bigger mass would cause a bigger resistance. But it also depends on the location of the mass, where the mass is. And we found out that that's actually related, it appears, to a square in the radius, not to just a change in the radius.